canal portion may be a line canal. But in the catchment, say upstream area, there may be lot of hills, or there may be vegetation cover may not be there in the catchment area, and because of that, during rain, suppose lot of sediment may come. So although our canal is a line canal, but it is carrying a sediment-laden water. It is carrying sediment-laden water. And now if the flow velocity in the canal become very less, then the sediment carried by the water may start settling down in the canal. And as we know that, say this is our canal, and from the upstream, say a lot of sediments are coming, and then sediments are settling down because the flow velocity is less. And for a water, its sediment carrying capacity depends on the flow velocity. Well, if its velocity is high, it can carry more sediment. Suppose the water are coming from the upstream catchment or the upper catchment, where it is coming from a hill. On that way, suppose the slope is very high there and the flow velocity is very high, it is eroding the soil, and then it is coming and it is entering the city, and in the city it is finding a drainage canal where the flow is moving, but that flow is carrying a lot of sediment that it has carried from upstream. And once it is in the city, it may be a plain area, and if it is a plain area, of course in the city, if it is hill, that is fine, velocity may be high. But if it is a plain area, then if the velocity drops below a particular limit, then depending on the size of the sediment, it may start settling there. And if it settles, then the carrying capacity of the canal will be reduced. Say originally its sectional area was entire sectional area. With time, when sediment will start settling there, then its carrying capacity will be reduced grossly, and then the objective for which the canal was designed will not be served. So that way, we need to take care that when we are designing a channel, suppose we have done our calculation, we have put the best hydraulic section, then what we need to see that for the required discharge, with what velocity the water will be flowing in the best hydraulic section. Now in the best hydraulic section, suppose we are finding that with the velocity with which the water is flowing is not sufficient to carry the sediment that it is carrying with it, then definitely we cannot provide the best hydraulic section, because at that point our criteria changes. Well, we tried with best hydraulic section, but it cannot be provided because the water will not be able to carry the sediment, and sediment deposition may take place. That will create problem. In fact, in a city, I was involved in a drainage design, and I could see that this canal, the existing canal, could not serve because the total depth is 1.5 meter, but this depth of sediment that was observed is 0.5 meter. So originally it was designed for 1.5 meter of depth, but this existing depth is only 1 meter. So that way, this lead to flash flood sort of things. That is, the canal cannot carry the required drainage, and then we had to see that how it can be overcome, how this problem can be overcome. So this design was wrong actually. So that sort of concept we need to see. Then another point, that constraints of not exceeding maximum permissible velocity. This is also one point. Of course, in line canal, if our lining are strong enough, then we can go for high velocity. Even in some cases, we can go up to 3 meter per second, 4 meter per second. That sort of velocity is also permissible. But if our lining is not that strong enough, say due to economic reason, we cannot provide that strong lining. And in that case, we'll have to be worried about that aspect also, that the velocity should not exceed a particular limit. And so far as minimum velocity is concerned, it is generally found at 0.6 meter to 0.9 meter per second sort of things. And in an average, generally 0.7 meter per second can be considered this minimum velocity so far is concerned. But maximum velocity we can go to say 4 meter, 5 meter, depending on the type of bank lining. But this is one consideration that we need to make. Then there may be some other constraints, like constraints regarding width of the canal. Well, recently I was involved in the design aspect of one city called Dibrugarh, their design of canal, and then the drainage canal. This was found that with all calculations, that how much the charge will be coming from hydrological calculation, that I could see that the size required for the canal is, say, if I go for the best hydraulic section, the width becomes 4 meter, 5 meter, like that in some places. Now it is passing through some already developed area and roads are there. So we need to provide the canal in those portions, because so for the surface terrain condition is there. This is the place where the water will be coming. But now the road size itself is not that large there. So you forget about the side canal or the roadside canal. So there we may not be able to go for that type of canal, which is say 4 meter wide. Well, in that case, we may have to reduce the width and we may have to increase the depth to carry that discharge. Of course, while doing those, then we need to see whether the flow velocity will be dropping down to a minimum value and whether this will lead to sediment deposition. If so, whether a pumping device is required. All those aspects will be coming. And of course, sometimes even we may think that, okay, if this is not possible reducing that part, we may have to make a canal, box canal, over which the road may be there. So under the road, we may have to have a box canal. So different options are there. Well, but still, that sort of constraint may be coming, the width of the canal, land availability, and all these things will be coming. And sometimes there is, suppose, a constraints against depth of canal. Well, that is also another constraint. Suppose after calculating the best hydraulic section, we have found that the width is 2 meter, depth is 1.5 meter. Fine. Well, we tried to put that, but we have seen that below 1 meter there is a, say, very important object like, say, oil pipeline, suppose, which is carrying oil, and this cannot be removed, this cannot be lowered at that point somehow. And then you cannot provide a depth of 1.5 meter there. So you'll have to restrict your width, depth. And similarly, suppose in a particular area, we are trying to make a canal which is of 2 meter depth, and then we have found that after 1.5 meter, there is a rock strata. Well, and then say it is a irrigation canal, and we cannot afford to say cut that rock and to because it will be quite expensive. So that way it may not be possible. So we may decide that, okay, this our best hydraulic section cannot be provided here. Rather, we will go for a depth of say 1.5 meter, because at 1.5 meter depth the rock strata is there and we cannot go below that. So that way there may be different practical constraints, and that govern the size of the channel. But our effort, our basic design concept for line canal is that we should try for designing it as best hydraulic section, which is the most economic section as well. Well, then we'll be discussing on line canal in detail, but before going to that discussion, let us discuss some of the issues briefly about unlined channel. Well, we'll be discussing that also in detail in different class, but still some of the very fundamentals or required things we'll be discussing here. When we talk about design concept of unlined channel, entire concept is different. Here we are not talking about best hydraulic section, or rather we can say that the most economic section is not the best hydraulic section here. So because the entire concept is different here. So there may be erosion or deposition. Well, when it is an unlined canal, so with flow velocity, there can be always erosion of the bed, and bed and side can be eroded. And once it is eroded at a particular point, then it is obvious that the canal will be carrying sediment-laden water. Once it is eroded, it will be carried by the water. So from upstream itself, it can carry, within the channel itself, it can erode, and it can erode side and bed. and then it can carry the sediment. Once it is carrying the sediment, again, if the velocity is low, at some point, it may again deposit the sediment. So what we can have, that this sort of channel, we are very much concerned about the erosion and deposition of sediment in that particular channel. Well, and if erosion occurs and if deposition occurred, already we have discussed, if deposition occurred, then the entire carrying capacity decreases. And similarly, it has, of course, far-reaching effects. Suppose that channel is of this type and somehow the flow velocity is dropping down and deposition is taking place here. Now, when deposition takes place, what happens? Suppose the water was flowing with a particular velocity. Now, when deposition is taking place, flow velocity get retarded in the upstream. And when it is retarded, because it is getting some obstruction and it is retarded flow velocity, if it as it is as a subcritical flow flowing here, so it is retarded. Now, when it is retarded, its sediment carrying capacity further drops down and then further deposition takes place. So that way, ultimately, the entire channel slope get reduced like that. When slope is reducing, again depth is increasing, flow velocity is further decreasing, and then sediment deposition is further increasing, and that way it is a progressive process. It leads to a progressive process, and that's why this is not desired at all. So we should design the channel in a way that there should not be deposition of this kind. Similarly, if it erodes the channel, then also we are not achieving our target. If it is eroding, then it will cause damage to the channel flow. If it is eroding the side, it can get widened. Suppose a channel is like this, was like this, and it has eroded this side and bed, then its entire section is changing, and we may not get the required depth what was desired, and the flow velocity may again change. And then again, it may sometimes lead to deposition, initially erosion. So those erosion and deposition, erosion will always cause damage to the channel, and that's why this erosion and deposition we should not allow, or we should design our channel in such a way that this can prevent erosion and deposition, which is not desired at all. Well, and that's why it is required to design a canal to carry the required discharge. Discharge is always fixed. We are deciding that our channel is to carry this much of discharge. So this discharge safely. By safely, what we are meaning? That maintaining the required dimension of the channel. Maintaining the required dimension of the channel means it should not get eroded, neither there should be deposition. Well, so thus design principle is to have a flow velocity which will neither cause covering, means that is erosion of the bed, nor will allow sediment deposition, Well, in the bed. So this is what the design criteria. So in our design of line canal, the design criteria was that it should be the best section, most economic section. But here our design criteria is that in unlined canal, the design criteria is that the velocity should be such that there should not be any scouring, or neither there should be any deposition. Of course, in real situation, it may happen that the bed is having some erosion, because the process of flow is like that, it may cause some erosion in the bed. And at the same time, it is eroding, the water is eroding some part of the soil, and again deposition is taking place in the next moment in that position. So erosion and deposition process, if it is going simultaneously, in that case, it will appear that the channel is neither getting eroded nor it is getting scoured. But in reality, both process may go parallelly. Well, in some of the design concept of unlined canal, it is assumed like that, that we talk about a critical velocity, that this is the critical velocity. Well, this critical velocity is different from the critical flow concept that we discussed earlier, that is the minimum energy concept. It is not like that. But we talk about a critical velocity, it is like that, which is neither scouring nor depositing. Or we can say that it is covering and depositing, but both are in balanced condition, and that's why it is appear to be neither scoring and nor depositing. So that sort of concept will be coming. Again, when we are talking about unlined canal, then the canal that we are designing as unlined, it may pass through a alluvial formation or a non-alluvial formation. Well, when it is passing through a non-alluvial formation, means a clay formation and like that, so that sort of formation is less susceptible to erosion. And in that case, our major criteria is, say, there should not be deposition, or the velocity, or rather one point is that this alluvial, it is non-alluvial canal, then we can decide that if the velocity is not exceeding that particular limit, which can cause erosion to this unlined canal, non-alluvial unlined canal, that we should not cross that velocity. So it is a maximum permissible velocity concept we can follow. That this is the maximum permissible velocity. We should decide the shape, we should design the shape in such a way that we achieve a velocity which is not crossing the maximum permissible velocity. And at the same time, the minimum permissible velocity is also there, which will not allow a deposition of sediment. But if it is passing through a alluvial formation, in that case, we need to go for that critical concept. Erosion and deposition both are very much important there and relevant for the design purpose. And for that, actually, the theory developed so far is not that much. And most of the things are empirical. That is based on the observation carried out in different canal. Some formula has been derived. That is, empirical relations are there. Of course, semi-empirical theories has also been developed. That is semi-theoretical, we can call. Well, that way different concepts are applied for design of unlined canal. Well, now till now we are talking about one term, that is most economic section. Well, but what this most economic section is, we have not discussed till now. We are giving just one term, that is the perimeter should be minimum. But why? That we have explained. But if perimeter is minimum, how we can achieve this? How we find that what condition will lead to perimeter minimum? So let us see that concept of most economic section. Well, we discuss about a term called conveyance, that is Q is equal to, say, 1 by n a r to the power 2 by 3 and s to the power half. And when we design canal, we are talking about normally uniform flow. We see that in uniform flow condition what it is. And then of course when we decide the site, we give some excess height, that is called freeboard of the canal. And that freeboard is given, generally it should not be less than 5% of the depth, or it should not be more than 30% of the depth. It depends on some other criteria based on which we decide that this should be the freeboard. So from our design depth, we give some excess depth as freeboard. Well, that will be coming, but normally we use uniform flow formula. So this is what the formula. And here 1 by n a r to the power 2 by 3, that is basically the conveyance K. And when our conveyance is more, that means it can carry more discharge. Conveyance more means, well, literally it means that it can convey more water. So our target is to maximize the conveyance. Now when this SB is fixed, N is, suppose we have decided from the other criteria as discussed, then our target is to minimize this a r to the power 2 by 3. Or now we can write from here, say this is equal to 1 by n a, then a by p to the power 2 by 3 and sp to the power half. Now as we were talking about other criteria, say area is fixed, means if our area is fixed for a particular length, volume is fixed. Now so when for that particular area, and say we want to maintain a velocity, then also we can see that which area is sufficient. So discharge is given. We know that discharge by area will also give us the velocity. So from that point also we can roughly see that our area should be this much, or that way also we can decide. Now area is suppose fixed, then how we can maximize this Q value? For the given area, we can maximize the Q value, our required discharge for a given SB, for a fixed A, then our required discharge can be maximized by minimizing the perimeter, okay? So that is what our basic concept. And now we know that, say, perimeter minimization, how we can get the perimeter expression if we write, suppose for rectangular channel. Say, let us say for rectangular channel. Okay. For rectangular channel, this is the B bed width, and then this is what is depth Y. Now perimeter is equal to, we know that B plus twice Y, okay? B plus twice Y is the perimeter. Now, of course, we want to minimize this P, and for that we want to see that how we can express B, because that our area is important at this point. So we can see how we can express it, that area is equal to B into Y, B into Y. So this implies that B we can express as area by Y. Well, so B we can write as area by Y. Now, so P is equal to, so we can write it as A by Y plus twice Y. Now, if we consider P, now we can consider P as a function of rather Y, because we are already considering that A, we are targeting that A is fixed, and then we are trying to find P as a function of Y. So how we can have minimum P? If we do, say, dP dy equal to 0, then this will give us the minimum perimeter. This expression will give us minimum perimeter. So we can just write that our expression was P is equal to A by Y plus twice Y. Now if we just use that concept, the dP dy is equal to 0 implies that A is fixed, so it is 1 by A, so it will become A into, say, 1 by minus Y square and plus 2. This is equal to 0. So this will imply that A by Y square is equal to 2. A by Y square is equal to 2. Now again we know what A is. Area is nothing but B into Y. So just replacing that, what we can write, BY by Y is equal to 2. That implies that if we BY by Y square, that was okay. So this and that will go. So B is equal to Y. Earlier we were just using the term I was talking about, say our expression is for most efficient section or for most economic section, our relation is that B is equal to twice Y, that we were just saying. Now we have seen that if we go by this particular concept for rectangular channel, we are getting that B is equal to twice Y